One of the reasons I think I'm still in Swansea is because of those beautiful views and being by the sea. I think I'd miss living by the sea if I wasn't living by the sea anymore. Anyway, this week I'm going to talk about what it is. The pancreas. We're going to talk about the pancreas. So we've been doing various gastrointestinal tract stuff the last few weeks. There are a whole bunch of accessory organs or associated organs of the GI tract and the abdomen. Let's have a look at the pancreas. It's another one of those organs that's absolutely vital for life, but you might not know where it is or exactly what it does. So, the pancreas. Let's have a look at its structure, its parts, where it is. We'll have a look in the abdomen, see what is around it, so that if you're then looking maybe at transverse CT scan images or transverse MR images, you can work out where the pancreas is, because it's kind of just a squidgy bit of tissue, squidgy bit of soft tissue, but you can work out where it is in relation to the other organs around it. We'll look at the blood supply. We'll look at where it is in relation to the GI tract. We'll talk about its exocrine function, its endocrine function. We'll have a little look at the histology, a little look at the cells, and the ducting and stuff, and we'll talk about what happens when it doesn't work quite how it should work, shall we? So let's have a look, see where it is first. You can see the lab's got a bit of a funky setup today. We're in the middle of a formative exam week for the first years, so the room is set up for OSCEs. You know OSCEs, like clinical skills exams? So they've got going to be poking and prodding each other and actors and that. Anyway, that's tomorrow I think, so I better tidy up after myself. Right, there's the liver. So we're taking the liver out. Remember, the liver is wrapping around the inferior vena cava. So the inferior vena cava is going up there into the heart. Here's the stomach. Notice we've got the diaphragm here. So we've got a series of ribs here. Look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's the spleen around here, right? 9, 10, 11th ribs. So you see the level we're at. If we take away the stomach, now we see the pancreas. Here's the pancreas here. Right, so there's the large colon there. There's the greater omentum on that side. Here's the pancreas, and here's the spleen here. The esophagus is just poking out there. This is kind of diaphragm curving around behind it. If I take off, so if I'm taking off the pancreas, look, here's the left kidney here, there's the left adrenal gland. So the pancreas is cutting across the upper half of the left kidney, isn't it? Right. And notice how here we've got the abdominal aorta and the inferior vena cava, and these are the branches of, look, there's the celiac trunk, there's the superior mesenteric artery, there's the inferior mesenteric artery there. So the pancreas is overlying all of that stuff. And most of these things, so the stomach and the large intestine and the small intestine, of course, are within the peritoneal cavity, or within the greater sac. Where's the pancreas in relation to the peritoneum then? Well, it's retroperitoneal. So the peritoneum is covering the pancreas and it's covering the kidneys. And the stomach is then attached to the spleen and the posterior abdominal wall by mesentery. So the stomach is within the peritoneal cavity, but the pancreas is retroperitoneal. And we can see, here's the duodenum here, and it's curling around, and we can't see all of it because the large intestine's in the way, but the pancreas is nestled into the curve of the duodenum. So the duodenum is partly retroperitoneal and partly in the peritoneal cavity. We can see up here, there's the celiac trunk, and it's giving off some blood vessels there. So if I take this model, which is some of that stuff taken out, right, you can see there's the pancreas here, and there's the duodenum curling around it. And the duodenum is really important to the pancreas. The pancreas is really important to the duodenum. The pancreas itself has a head at this end and what we call an uncinate process, which is difficult to see here, but there's a bit of pancreatic tissue hanging down here into the curve of the duodenum. So it's got the head and then the neck, and then the tail of the pancreas extends out into the hilum of, this is the spleen here. And we can see the blood supply to the pancreas quite nicely. This is it here. Now, as I said, that's the celiac trunk, which is here, coming out of the abdominal aorta. And the celiac trunk then is giving off a number of arteries, but one of its arteries is this one here. This is the splenic artery, and clearly it's supplying blood to the spleen over here. But the splenic artery is running along the superior edge of the pancreas. And in fact, when we look at this in cadavers and in people, we see that it's kind of wiggly. It's kind of a wiggly artery, and it's maybe a little bit embedded in the tissue around here. And just on the other side there, posteriorly, here's the splenic vein draining blood from the spleen back to the portal vein. In fact, the portal vein forms as the splenic vein joins with the inferior mesenteric vein here, and there's the superior mesenteric vein joining with it. So the blood supply to the pancreas then is from the celiac trunk. We do have these pancreatico-duodenal arteries here looping around, and we've got superior and inferior, and we've got anterior and posterior. They're largely supplying blood to the duodenum as much as anything else, but obviously they're probably going to be supplying blood to the head of the pancreas and the uncinate process as well. But it's this splenic artery here that's sending off lots of little blood vessels into the pancreas, and that's supplying blood to the pancreas. And then the splenic vein is draining blood from the pancreas. And that's really important because the pancreas, it chucks out a load of hormones, right? So it does stuff with the blood and does stuff with other bits of the body. Which leads us into the functions of the pancreas. So if we look at the cells within the pancreas, we find two types of cells, two groups of cells. We find that most of the pancreas is made up of exocrine cells. So exocrine means to be secreting through a duct onto an external surface. And in the case of the pancreas, it's these exocrine cells are producing a secretion that's secreted into the GI tract, and the GI tract, the gastrointestinal tract, is considered an external surface within us, right? An external internal surface, right? There's a tube running through us, open either end. See what I mean? Most of the cells of the pancreas are making pancreatic juice, this exocrine secretion that's secreted into the duodenum, and that aids with digestion. And then within the pancreas we see clusters of cells, little islands of cells, which get called islets, or islets of Langerhans, after the guy that first described them. And in those islets we find endocrine cells, and those endocrine cells are secreting hormones. So endocrine means to be putting something into the blood that affects other parts of the body. So the endocrine cells, we've got alpha cells, beta cells and delta cells. They're the ones right to start with. Alpha cells produce glucagon, beta cells produce insulin, and delta cells produce somatostatin. So this leads us to probably the most famous function of the pancreas, and that's regulating blood glucose. So glucagon is secreted when blood glucose levels are low, and they encourage the release of stored glucose, as in glycogen, to be released from things like the liver, where glycogen is stored, into the blood. So the glucose levels come up again, right? Because you use glucose as an energy source for all your cells around the body. Insulin does the opposite. So you just had a big meal, all that's being digested, you've got loads of glucose in your blood. Insulin goes into the blood and tells all the cells of the body, liver and other things as well, to take that sugar and store it away. Store that glucose as glycogen for a bit until we need it. So that then brings the blood sugar levels down. So glucagon and insulin work in opposition to manage blood glucose levels. And obviously there are other parts of the body involved in this. But it's in type 1 diabetes where beta cells of the pancreas are destroyed, it's usually an autoimmune thing, right? And someone then doesn't have enough beta cells, doesn't produce enough insulin, so then they have to do this manually. They have to manage what they eat, and they have to inject insulin regularly to manage their blood glucose levels themselves, which is an arduous process. You have to measure your blood glucose and keep track of that, and it's a bit of a pain. Type 2 diabetes is different. That's where the cells of the body start to become a bit indifferent to insulin and just say, we see sugar all the time, it's cool, don't worry about it, and you get a whole bunch of other problems. But type 1 diabetes is caused by a loss of beta cells in the islets in the pancreas, so you can't make enough insulin. Now there are also gamma and epsilon cells. Now somatostatin produced by the delta cells, generally it suppresses the production of all the gastrointestinal hormones. So we talk about the GI tract and the pancreas as well. They're innervated by sympathetic and parasympathetic nervous systems, and we talk about the parasympathetic nervous system as being involved in rest and digest functions, right? So parasympathetic innervation stimulates the GI tract to digest stuff and absorb stuff, right? But in fact, a lot of these organs and a lot of these secretions and a lot of the control is actually endocrine. So there are hormones secreted, and these balances of hormones, we've got the pituitary gland and other bits of the body, they all work together in concert to manage the activity of the GI tract. So somatostatin will slow down the activity of the stomach and hormones being produced by other parts of the GI tract and that sort of thing. So you've got, and the somatostatin will also affect the production of glucagon and insulin, right? So we've got all these. Right, if I start talking about physiology, we will be here all day. The gamma cells make pancreatic polypeptide, which also regulates activity of pancreatic endocrine cells. And the epsilon cells make ghrelin. Ghrelin is most famous as being like the hunger hormone, regulates appetite, right? So is it if you've got lots of ghrelin, you feel full, you feel saturated, you feel, something like that anyway. But yeah, so those are the endocrine cells of the pancreas within the islets of Langerhans. Now the exocrine cells, so they're kind of, we've got these secretory cells kind of arranged in like around an acinus, right? It's kind of on a curve, and they're secreting into a space, and then what they secrete into, that space goes into a duct, and that duct goes into other ducts and other ducts and other ducts, and eventually you see this duct here. So this is the main pancreatic duct running the length of the pancreas. We've got this herringbone shape because we can see the other ducts ducting into it. The exocrine secretions of the pancreas are things like trypsin, chymotrypsin, amylase, and we've talked before about how trypsin and chymotrypsin are proteases, so they break down proteins. You're made of proteins, so proteases are quite dangerous to you, right? So we've got a tissue secreting dangerous things that could break the tissue down. So they're secreted by the cells, and they're packaged up nice and tidily in an inactive form, and then they pass along the main pancreatic duct and are secreted into the duodenum here, and it's in the duodenum that they get activated. Again, more physiology. You want to know how? That's another day. So these enzymes, ideally, they get activated in the duodenum, and then those proteases can break down the proteins. We've also got pancreatic lipase that's going to break down fats. We've got amylase that's going to break down starches into what? Maltose? We've got gelatinase, elastase. You've got deoxyribonuclease and that sort of. So there's a whole bunch of things being secreted by the pancreas that help with digestion in the duodenum. That's the important bit, right? So these exocrine secretions from the pancreas secrete into the duodenum. Now, can you see there's two ducts here? So there's a main pancreatic duct, which is actually the inferior one, the lower one here. And then there's an accessory pancreatic duct here, which is a little diddy one. Now, this occurs because in the embryo, there's a simple gut tube, right, and it's held in place by, up at the level of the stomach, there's a posterior, like a dorsal mesentery, which we call the mesogastrium, gaster, because it's next to the stomach. And there's a ventral mesogastrium, because it's at the level of the stomach, between the future stomach tube and the anterior abdominal wall. And then we see a couple of buds growing from the early GI tract, and those buds go on and form various things. They form the liver and the gallbladder, and they form two pancreases. So there's an anterior pancreatic bud and there's a posterior pancreatic bud, or dorsal and ventral if you like. And then the stomach, right? The stomach rotates around and pulls the duodenum with it and stuff like that. And when it does that, it brings these two pancreatic buds around and they meet together. So that's why when we look at the adult pancreas, we see two ducts, because really the uncinate process down here, that's kind of the other bud right? The little bud, and this is the big bud, the big pancreatic bud here. And those two pancreatic buds have been brought together, and they had their own duct because that's how they formed. They ducted from the GI tract, and then you formed. Basically, this is endoderm, because this is the GI tract, so endoderm is forming the innermost layer, and then the cells of the pancreas are formed from endoderm. They follow different differentiation pathways, whether to become exocrine cells or endocrine cells, and then further differentiated into becoming all those different cells we've been talking about. Anyway, so this main pancreatic duct in most people collects most of the exocrine secretions and ducts into the duodenum here. There, and the other thing is, right, you see the green tube here? Now I said that the gallbladder and the liver also grow out in the same outpouching, right? So there's another tube connecting the gallbladder and the liver, because bile comes from the liver, right, and then backs up and gets stored in the gallbladder. Anyway, this is the common bile duct. So the bile duct also loops around. The bile duct and the main pancreatic duct both duct into the duodenum at the same point through the same hole. Now the common bile duct has its own sphincter of smooth muscle, which it can close off, and the main pancreatic duct has its own sphincter of smooth muscle, which it can also close off, but it's obscured by this blood vessel here. But just before those two ducts come together and duct into the duodenum at the same place, there's an ampulla. So an ampulla, ampule, right? You know, it's you got a tube and it kind of, you know, right, ampulla, kind of a little bit of a dilation of a tube. So there's a hepatopancreatic ampulla as those two tubes meet, which used to get called the ampulla of Vater, and then they both, around the ampulla of Vater, or the hepatopancreatic ampulla, there's another smooth muscle sphincter, which is the hepatopancreatic sphincter, or the sphincter of Oddi, which is a great name, but it is its old name. So all those sphincters then can control the flow of exocrine pancreatic juice into the duodenum and bile from the common bile duct into the duodenum. And that's what we see in about 90% of people. We see that organisation. And this accessory pancreatic duct up here just drains its pancreatic juice into the main duct and it pops out there. But in about 9 or 10% of people, you'll see a second opening up here in the duodenum. This is the descending or second part of the duodenum, by the way. And there will be the accessory pancreatic duct will open at an accessory papilla. So there's a little papilla, right, a little mound in here where the main pancreatic duct opens. And in some people, and in fact on this model, there is a second opening there. So if you're doing, you know, an endoscopic process and you're looking down the duodenum and you find one opening and then you find a second opening, that's fine. It's not terribly unusual. So that's how the exocrine secretion of the pancreas gets into the duodenum. The endocrine secretion goes straight into the blood. Alright, so that's some of the functioning of the pancreas. Now, we were looking at structures nearby. There's another cool thing to notice. So you remember that the abdominal aorta is running just posterior to it, and we can see the celiac trunk here. Now that we've talked about the duodenum curling around and the pancreas running across, can you see here? Look how the superior mesenteric artery and superior mesenteric vein appear from between the pancreas and the duodenum, and then they run anteriorly. So that's another good landmark. That's how you find the superior mesenteric artery, right? Oh, also, the epithelial cells of the pancreas make bicarbonate. Stomach makes acid, bicarbonate neutralizes the acid from the stomach, comes from the pancreas. So what could go wrong with the pancreas then? Well, we've already talked about diabetes and loss of the beta cells, loss of the ability to produce as much insulin as you need. Actually, from a tissue engineering standpoint, now that you know about the embryology, it would be possible, wouldn't it, to take embryonic stem cells and then differentiate them into endoderm and then into like down a GI tract pathway and into pancreatic cells, and if you could work it out, you could cause these cells to differentiate into beta cells, and you could take your population of beta cells and say inject them into the portal vein, and they would seed the liver, or something like that, and then the patient would have beta cells and they could produce insulin. Would that be a cure for type 1 diabetes? Maybe. People have already tried that and it seems to be working. I think the latest idea is to package these cells in a different manner and put them under the skin and what have you. But cool, huh? Tissue engineering, you've got to understand the embryology and blah 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 blah. So that's type 1 diabetes. Now, because the bile duct and the main pancreatic duct are duct into the duodenum at the same place, you've heard of gallstones, right? So you can get stones in the biliary tree in the bile duct. You get them in different places, and it's possible, of course, that the bile stone, if it's formed higher up, could move down the common bile duct. So it's possible that you could get a gallstone lodging in here, say in the hepatopancreatic ampulla, which would not only prevent bile from going into the duodenum, but it would also prevent exocrine pancreatic juice from passing from the pancreas into the duodenum. Now, what do you think that would lead to? Well, you'd get, you wouldn't be able to get rid of all the bilirubin from the liver, so you start to get rising levels of bilirubin, so the colour of the skin would become yellow, would become jaundiced, right? So you'd see some liver dysfunction, but also you'd start to see signs of acute pancreatitis, so you'd start to get inflammation of the pancreas and damage to the pancreas, which would be bad. You can get acute pancreatitis for other reasons as well. So, I said that we've got these dangerous proteases, these enzymes which could digest tissues, proteins of the pancreas, and they're packaged up and then released safely into the duodenum. Well, if that process is broken down, if that packaging isn't made correctly, if those proteases, if those dangerous enzymes aren't safely packaged away, then they can damage the pancreas. And then you'll see inflammation of the pancreas, and again acute pancreatitis, and you kind of get this pain developing and this sort of thing. So acute pancreatitis is dangerous, and it has something like a 10% mortality rate, so it's very dangerous. And you usually get like an onset of mild pain, which gets worse and worse and worse. The pain gets worse with eating. Makes sense, because of course you've got all the triggers to make your pancreatic juice and secrete it and put it in the duodenum, but it can't get into the duodenum, and it's damaging the pancreas, right? So pain increases. People tend to be very, very ill with acute pancreatitis. You have to go to the hospital and often get a nice surgeon to help you out. So acute pancreatitis can be caused by a couple of things. Think gallstones here, and think poor packaging of those dangerous enzymes. So that might be a result to use of a certain drug, or alcohol, or something like that. What else? Oh, pancreatic cancer. Pancreatic cancer is very, very dangerous. Acute pancreatitis can be difficult to diagnose because there's a lot going on around here. Pancreatic cancer, likewise, can be very difficult to spot and to diagnose. If the cancer forms up here somewhere, then the pancreas is probably functioning just fine, and there are very few signs that there's a tumour forming in the pancreas, and the tumour can spread quite easily from the pancreas. Now, if the tumour forms in the head of the pancreas, that's better, because it's going to block the ducts down here and may lead to signs of acute pancreatitis and jaundice much earlier. So you get an early sign of a problem, and then you can hopefully diagnose pancreatic cancer and remove it early. But the reason pancreatic cancer is so dangerous is because it'll often form in the tail of the pancreas and give virtually no warning signs at all, and it'll get larger and spread. So it has a very high mortality rate. I think does it get called the like the silent cancer, or silent cancer, something like that. So pancreatic cancer, very, very dangerous. So how's that? We've looked and seen to see where the pancreas is. So if you're looking at transverse section of the abdomen on CT or MR, for example, then look for the pancreas posterior to the stomach. The stomach you might see as as a dark space with air in it. Anterior to the aorta. You should be able to spot the aorta and the inferior vena cava, anterior to the kidneys. Those are your landmarks, right? So anterior to the left kidney there. And if you've got the spleen in your section, you're probably too high. We've talked about the functions of the pancreas. Generally, there's a huge amount of physiology going on there, but that's somebody else's job. We've talked about what can go wrong with the pancreas. We've talked about the blood supply. I briefly talked about the innervation. So there's parasympathetic and sympathetic innervation of the pancreas, but most of the control of the pancreas is endocrine. It's under hormonal control. Parasympathetic innervation is through the vagus nerve, of course. Everything's through the vagus nerve down here. And there you go. So quick overview of quick. Yeah, when do I ever do anything quick? Look at the anatomy of the pancreas. Hopefully it'll serve you in good stead. Right, what's left in the abdomen to talk about next time?